Bismillahirrahmanirrahim. Electromagnetic field theory. And in the last lecture, we have studied how to find the electric field intensity and the electric potential due to a point charge. But now, in this lecture, we have to find the electric potential due to a system of charges. So, let's suppose we have a single charge Q, which is placed at a distance of r1 from the origin, and our point of observation is P, which is at a distance of r from the origin. So and the position vector from the source charge to the point of observation is capital R, which is equal to R minus R1. So uh, now the electric potential at a point P due to the source charge is given by Vp is equal to Q divided by 4 pi epsilon naught R. We have already derived this relation in the previous lecture. So now in this lecture we have to apply this relation for the system of charges. So okay, so Vp is equal to Q divided by 4 pi epsilon naught R minus R1. Now consider the n number of charges in the free space. We need to calculate the electric potential at the point of observation due to all of these charges, that we have a charge q1, q2, q3, and so on up till the qn. And the position vectors for each of these q1 charges are r1, r2, r3, and up to rn respectively. So according to the superposition theorem, the whole system of charges will be added to get the net electric potential of the system. So the electric potential due to the charge q1 will be represented by v1 is equal to q1 over 4 pi epsilon naught r minus r1. Okay, so similarly for charge q2, the only difference will be the q2, and r minus r1 will be replaced by r minus r2, because the position vector of the r2 for the q2 is given by the r2. So similarly for q3, we will have electric potential v3 is equal to q3 over 4 pi epsilon naught r minus r3. Okay, so up till vn. Okay, for the charge qn, the electric potential will be represented by the Vn, which is equal to Qn over 4 pi epsilon naught R minus R1. Okay, so according to the superposition theorem, the total potential at the point P due to all of these charges is given by V is equal to V1 plus V2 plus V3 plus up till plus Vn. Okay, so write down the values of each of the electric potential V1, V2, V3. V1 is given by this relation, V2 is this, V3 up till Vn. So apply the summation formula. Okay, now we are introducing the variable Vm. M is the variable which which will represent the summation of the whole system. Okay, so the m ranges from 1 up to the n. Okay, so the equation for the net v after applying the superposition theorem will be given by qm or 4 pi epsilon naught r minus rm. Okay, so the values of rm ranges from 1 up to the n. Okay, so first we have to put the value of m is equal to 1 q1 divided by 4 pi epsilon naught r minus r1. Similarly, then put m is equal to 2. So we will get this relation by putting m is equal to 3. We will get this, and by putting m is equal to n, the last ones we will get this. So by this way, the electric potential of the system of charges will be find out. Okay. Now switching towards the electric potential due to the line charges which are distributed along the line ranging from minus infinity to plus infinity. So graphically you can see that the charges are distributed along the z-axis. It is not necessary to represent it along the z-axis. This is just an example. You can represent it along the x-axis and as on the along the y-axis as well. Okay, so here the book have represented it along the z-axis. So it ranges from minus infinity to plus infinity. So this is the origin. The point of observation is at a distance of r from the origin, while the differential length we have assumed over here is at a distance of r1. Okay, so now the distance between the differential length of the line charges and the point of observation will be r minus r1. Okay, so as mm, as you as you can see that uh, here the charges are distributed along the length, so we have to introduce the line charge density. Okay, so the line charge density is equal to rho l is equal to q over l. Now the differential voltage due to the segment of the differential length distributed along the line is will be represented by dVp. This d represents the small differential voltage in the differential length dl. Okay, so dVp is equal to deq over 4 pi epsilon naught r minus r1. Okay, now we have to replace this q with the line charge density, because now the charges are distributed along the line. So the point charge will not be valid over here. So replace it by line charge density VL into DL over 4 pi epsilon naught R minus R1. Okay, now to find the net potential of the whole length, apply the integration. Okay, so here is the integration. VP is the net potential of the whole length, integration rho L dl over 4 pi epsilon naught r minus r1 absolute. Okay. Now similar is the method to find the electric potential due to the surface charges. So now we have to consider charges in the form of a surface. Okay, ds S is the whole surface and ds is the small portion, differential portion of this whole surface. Okay, and the charges the charge density will now be surface charge density rho s. Okay, so in this case we have to replace the dq, this the point charge, by surface charge density. Okay, r is the position vector of the point of observation, r1 is the position vector of the differential charges from the origin. Okay, so the distance between the source charges and point of observation is r minus r1, similar to the previous case. Okay, so dq is equal to rho s ds. So replace dq by rho s ds in order to introduce the surface charge density. Okay, so dvp, d is the differential potential of the differential surface. Okay, now to integrate the whole all the differential surfaces to get the complete the complete potential, the net potential of the complete surface. So this here is the limits of s. Okay, integration of s rho s ds over 4 pi epsilon naught r minus r1. Okay. If you have the surface in separate dimensions, so we will apply double integration. Okay, one for the length, one for the breadth. Now similar is the case with the volume charges. Can now consider a charge of the uniform density in the form of volume, and the volume density is known. Okay, so we need to find out the absolute potential at a point of observation due to the volume charges. So these are the volume charges. Now consider a differential volume dv. Okay, which is at a distance of r1 from the origin, and point of observation is similarly r from the origin. So distance between the source charge and point charge is r minus r1. Now consider a differential portion of the volume charges. So let R1, as I have told you, R1 is the position vector of the differential, and R is the position vector of the point of observation. Okay, so dq is equal to rho v dv. Now we have to replace dq with the rho v in order to introduce the volume charge density. Okay, so the differential potential at the field point is given by dvp is equal to dq divided by 4 pi epsilon naught r minus r1, replacing dq with rho v dv. So rho v dv divided by 4 pi epsilon naught r minus r1. Okay, applying the integration to get the net electric potential of the whole volume charges. So vp will be equal to rho v dv divided by 4 pi epsilon naught r minus r1. Similarly, if we have separate dimensions of each volume, so we will apply a triple integration for each of the dimension. Now a few example based on these electric potential, which is very simple. We have to find the electric potential at a point p. P is a point of observation which is along the z axis, as given p 0 comma 0 comma 10, which means the x-axis 0, y-axis 0, and z is 10. So it means the point of observation is along the z-axis. Okay, the A part is 20 nanocoulomb at origin. The point, the source charges, the source point charge is at the origin. Okay, in B part, the charges are distributed along the y-axis. Okay, -1 to +1. And in C part, we have 10 nanocoulomb per meter along the line, along the z-axis. Okay, so let's start with the part number A, which is very simple. As the point of observation is along z-axis, while the source charge is at the origin. So it is very easy. This is 10, and this is at 0 because the origin. So the position vector will be 10 minus 0. Okay, which will be equal to 10. So straight away put the values over here. Vp is equal to q divided by 4 pi epsilon naught rp. Okay, so rp is 10, as find from here. Q 20 nanocoulomb, which is given. Okay, and 4 pi epsilon naught, this is the value of epsilon naught. So the electric potential uh, at point of observation 10 is given as 17.98. Now the point of observation in the B part, this is the figure for part B. Okay, you can see that the charges are distributed along the y-axis while the point of observation is along z-axis. So there will be issue because r is along z-axis while r1 is along y-axis. Okay, so what technique can be applied? Okay, find r minus r1. R is 10. Okay, r1 is y. So 10 square, which is 100, y square is y square, y square plus 100. Okay, now vb is rho l, because line charge density will be must be introduced over here. So rho l dl divided by 4 pi epsilon naught r minus r1. Dl is along y-axis. Okay, charges are distributed along y-axis, so dl will be dy. Okay, so and the rho l is given 10 nanocoulomb, so 10 into 10 power minus 9 dy divided by 4 pi epsilon naught. This is the value of epsilon naught, and r minus r1 absolute is given as y square plus 100 whole square root. Okay, now the rest of the constants are squeezed to get 89.91, and the limits are from -1 to 1. Now the integration of this is not possible, so for that purpose we have to convert this y in means RCS into a spherical coordinate system. So we have to into some trigonometric function so that our calculation makes easy. So let's suppose y is equal to tangent 10 cotangent theta. Okay, so mm replace find the derivative with respect to theta, so that dy may be converted to d theta. So 10, okay, the integration and the derivative of cotangent will be cosecant square theta. So cosecant, this is 10, okay, cosecant square theta. Okay, now multiplying d theta on both sides, so we will get dy is equal to tangent, sorry, 10 cosecant square theta. This is cosecant square theta d theta. Okay, so replace dy with minus 10, because okay, this is minus, okay, minus 10 cosecant square theta d theta, and y with this 10 cotangent theta. Okay, now the limits, because minus 1 and plus 1, these are the limits of the dy, but now for after introducing the theta, the limits will be changed. So we have to find the limits for the theta as well. So as we know that from this relation, y is equal to tangent 10 cotangent theta. So uh, cotangent theta will be equal to y divided by 10. Okay, so inverting cotangent theta is 1 over tangent theta. Okay, so inverting it, and also invert the right side as well. So tangent theta will be equal to 10 divided by y. The numerator becomes denominator, and denominator becomes numerator. Okay, now we have to find this theta. Okay, so theta will be equal to tangent inverse 10 divided by y. Now putting the y limits minus 1 and plus 1. Okay, minus 1 is the lower limit, and plus 1 is the upper limit. So now first of all find the lower limit. Okay, so putting y is equal to minus 1 over here, tangent inverse, okay, 10 divided by minus 1, so we will get minus 10, and tangent inverse of minus 10 will 95.71. After using calculator, you will get this. Okay, now putting the upper limit, which is y is equal to plus 1. Okay, so uh, here, so tangent inverse 10 divided by plus 1, which is equal to tangent inverse 10, which is equal to 84.28. Now the limits have been found. So now just put all these values of dy and y and the limits over here to completely convert the whole equation in terms of the theta. Okay, now it will be easy for you to calculate. So minus 10 cosecant square theta divided by 100 cotangent square theta plus 100. So okay, minus 10 cosecant square theta divided by 10 cosecant theta. 10 will be cancelled with 10, 1 cosecant will be cancelled with that square, so we will left with cosecant theta only. Okay, now uh, okay, so the integration of cosecant theta will be ln of cosecant theta minus cotangent theta. The limits, putting the limits of theta over here. First we will, okay, now first convert this cosecant into sine and cotangent into cos and sine, so that the calculation makes easy. Okay, so cosecant is 1 over sine, cotangent is cos over sine. Taking the LCM, sine theta is the LCM, so we will get 1 minus cos. Okay, now it is ready to put the lower and upper limit of theta in this equation. Upper limit is 84.28, so you can see that this is 84.28, 84.28. Okay, and these are the lower limit, 95.71, 95.71. Okay, after applying the ln and taking the subtraction, and after multiplying, you will get 17.91. This was part number B, and now part C. Part C is easy. The charges are distributed along the z, while the point of observation is also along the z. Okay, so it's easy because r minus r1, both of r and r1 having the same direction, az and az. The source charges are also distributed along the z, and point of observation is also along z. In the previous example, the problem was that the charges were distributed along the y-axis. Okay, look, and the source charges and sorry, the point of observation is along the z-axis. So that is why the solution was difficult, and we therefore converted it into the trigonometric form. But now in this case, no need to convert into the trigonometric functions, because it is easy. So r minus r1 will be equal to r 10 az minus z az, taking z common. So 10 minus z. Okay, so and for the absolute, 10 minus z whole square, which is equal to 10 minus z. Applying this formula, differential length rho l dl divided by 4 pi epsilon naught r minus r1. Okay, so uh, the integration of 1 over 10 minus z will be equal to ln of this, because the integration of ln of x. Okay, 1 over x integration is ln of x. Integration of 1 over x is equal to, with respect to x, is equal to ln of x. So here x is 10 minus z. So integration of 1 over 10 minus z will be ln of 10 minus z. Putting the values of z, okay, first one, so we'll get 10 minus 1, which is 9, 10 ln of 10, and now putting minus 1, 10 minus 1, so 10 plus 1, so which will be equal to 10 ln of 11. Okay, so we will get this. So these were the numericals related to electric potential, and we will study the potential gradient in the next part of our lecture. So stay tuned.